So let's summarize these subatomic particles with their names, their charges, masses, and then where they live in an atom. So we have electrons, protons, and neutrons that we discussed in the previous videos with the experiments to discover these things. When we talk about electrons, we tend to abbreviate it as an E with a negative charge on it. So that's kind of a shorthand for electron. It has a charge of negative 1.602 times 10 to the minus 19th coulombs. Or if we are very generally talking about that electron, we'll say that it has a charge of negative 1. A proton, which we will abbreviate as a P with a plus charge, has a charge of plus 1.602 times 10 to the minus 19th coulombs, or plus 1. And a neutron, which we'll abbreviate as N with a 0, has 0 charge. So because the electron and proton have equal but opposite charges, we can, in many, many cases, as in like nearly every case that we will deal with, refer to one as a negative 1 charge and the other as a plus 1 charge. The masses of these things are similar for the proton and neutron, but very different for the mass of the electron. Now, it's going to look a little bit different from how you might see it listed on the equation sheet. So, one, make sure that you check your units. These are all in grams, but I have also written the electron mass a little bit different so that you can see what the magnitude of it is compared to protons and neutrons. So electrons are super tiny in comparison. So that would be a mass of 0.0091 times 10 to the minus 24th grams versus a proton, which is 1.6726 times 10 to the minus 24 grams, and a neutron, which is, we say the same mass as a proton. It's not identical. It's 1.6749 times 10 to the minus 24th. So the model that we are at for an atom, based on the buildup of those experiments and where we ended with Rutherford, is that we have a nucleus that is made up of protons and neutrons. So I've got these drawn in slightly different colors. So there are little discrete particles with positive charge called protons, little discrete particles with no charge called neutrons, all in this like tiny core that we call a nucleus. And then the electrons are just out there somewhere. They're diffuse. We don't really know anything else about the electrons at this point, but we do know that most of what's happening is empty space. So this is our current understanding of what an atom looks like. And for specific elements, we can use electrons, neutrons, and protons to talk about the identity as well as other things related to that atom. So Z is the letter symbol that we use to talk about the atomic number, which is the number of protons in the nucleus, and it indicates identity. So something with 5 protons will always be the same element because the number of protons tells you the identity of that element. And the corollary here, if I give you an element, so let's say the element bromine, once you find out how many protons bromine has, because those are specifically related values, then you know how many protons every atom of bromine has. So we will use that atomic number with the periodic table to figure out which symbol abbreviation to use for an element because it tells us the identity. We use the letter A to be the mass number, which is the number of protons plus the number of neutrons. Right? Those are the most massive components of the atom. The electron is really tiny in comparison. So we can use number of protons and number of neutrons to think about how heavy an element might be. Now, because the identity is determined by the number of protons, we could end up in this scenario. So let's say that we have atom A and atom B. Atom A has 6 protons and 6 neutrons. Atom B has 6 protons and 7 neutrons. These two atoms are the same element because they have the same number of protons. And it turns out that 6 protons means that the element you have is carbon. Now, protons plus neutrons means that these two atoms have different masses, right? 6 plus 6 is 12 and 6 plus 7 is 13. So these two atoms, they are both carbon, but they are isotopes. That word isotope means that they have the same atomic number, so they have the same identity, but they have different masses because they have different numbers of neutrons. We will shorthand this in the way that we write element symbols, and so I have a whole thing here because we put stuff in specific places around the element symbol, and the place that we put that number means something. So generically, if I use the letter X to be the symbol from the periodic table, the placement of A, so a superscript to the left, that mass number. So if you see a number as a superscript to the left, that means it is the mass number. And the subscript to the left is the atomic number. Now, for obvious reasons, right, it's a little redundant to have the atomic number and the symbol because they mean the same thing, they tell you the same thing. Initially, we are always going to write that atomic number in. Eventually, we're just going to drop it, right? Because if you write the letter C, it means carbon, which means there have to be 6 protons. I don't need to also write the 6 on here. For now, please include it when you're asked to do isotope symbols, but eventually you're going to see that. We'll leave it off. So for this atom A and atom B, if I were to write this out, so both are carbon. I find in the periodic table that the symbol for carbon is just a capital C. And because it's carbon, the atomic number is 6. So both of these get a 6 as the left subscript. But atom A has a mass number of 12. So I put a 12 as the left superscript. And atom B has a mass number of 13. So I put a 13 as the left superscript. When we say these out loud or write it in a sentence, it's usually written as carbon 12 because the word carbon lets you find the atomic number and the symbol, and then the 12 tells you what the mass number is. So atom B would be carbon 13. Of course, we should do another example. So let's do cobalt 60. When I look up cobalt, it has an element symbol of capital C, lowercase o, and cobalt has 27 protons. So it has an atomic number of 27. So 27 is my left subscript, CO is my symbol, and cobalt 60, 60 is my mass number. So that's my left superscript. Another example is iodine 131. So 131 is the mass number, so that's my left superscript. And then when I look up iodine, it has a capital letter I for the symbol and an atomic number of 53. So those are isotopes. Isotopes have different numbers of neutrons. We also have ions where an atom can gain or lose electrons. So it's got the same identity, but it has a different number of electrons, which means that it has a different charge. So when it's a neutral atom, you have the same number of protons and electrons, right? Completely neutral. If you gain or lose electrons, then you now no longer have a neutral atom. So, right, we've said this. I'll just do a quick summary again. Atoms are generally neutral. It's the same number of protons and electrons. When you lose electrons, so if you have fewer electrons than you do protons, the charge is positive overall, and we call this a cation. So an example of this, lithium with a 1 plus charge, this lithium cation, would have 3 protons because it's lithium. Lithium has 3 protons. And if the charge is plus overall, then it only has 2 electrons. See if you can do this for magnesium 2 plus and aluminum 3 plus. I'll give you a hint. Magnesium has an atomic number of 12 and aluminum has an atomic number of 13. If you have an atom that has gained electrons, it now has more negative charge than positive. So it will overall be negatively charged, and we call this an anion. So it has more electrons than protons. Fluorine with a 1 minus charge, this fluorine anion. Oxygen with a negative 2 charge, and I have this one written out for you. So oxygen has an atomic number of 8. So if it has a negative 2 charge, it has to have 10 electrons to have that negative 2 charge overall. And nitrogen likes to form negative 3 ions, or negative 3 anions. So ion is the generic word, cation means positive, anion means negative. When we write symbols, we include a lot of stuff in here. So these charges, you can see that I've written all of them as superscripts on the right side of the element symbol. So I've just got a summary here of, for my element symbol, which again, my generic is just the letter X, what am I putting where? So the things that we have talked about so far, one is the mass number as the left superscript, which is number of protons plus number of neutrons. 2 is the atomic number, this left subscript, which we're going to write for now, but we'll eventually leave off. It's just the number of protons. The charge is the right superscript, which if you like having an equation for this, the number of protons minus the number of electrons. But don't forget that like negative, you're subtracting negative charges, right? Just look at how much positive charge you have, how much negative charge you have, and count it up from there. And then the only space we haven't filled in yet is space 4, so the right subscript. That will tell you the number of atoms present. So we haven't done this yet, but I do have an example. So like N2, that as I've written it here, that means 2 nitrogen atoms connected to each other. So just do a quick example that is 1 atom. So we're not going to have that space number 4 filled up with anything, but let's do a selenium 79 anion that has a negative 2 charge. So selenium, when I look it up, the atomic number is 34, and the symbol is capital S with a lowercase e. That means 34 protons, and that capital S lowercase e is going to be my symbol. So 34 goes at the bottom, the subscript on the left. That's my atomic number. Selenium 79 is, the 79 is my mass number, so that goes at the upper left, so my left superscript. And then the negative 2 charge is on the superscript to the right. Now, you don't need to do any of the other math that I've done on here in order to figure these things out, because we're given the charge and we're given the mass number. But you could figure out how many neutrons and how many electrons it has, and we're going to do some problems where you may be given the number of neutrons, given the number of electrons, and asked to determine the charge. So if I have a mass number of 79 and an atomic number of 34, whatever the difference is has to be made up of neutrons, right? That mass number is protons plus neutrons. So 34 protons plus some number of neutrons gives me a mass number of 79. Well, that only works if there are 45 neutrons. So if I needed the number of neutrons, I now know that it's 45. The number of electrons, if selenium has 34 protons, then a neutral selenium atom has 34 electrons. Now, if it has an overall negative charge, that means it has more electrons than the neutral atom. And it has 2 more because it has a -2 charge. So neutral would be 34 electrons. This atom has to have 36 electrons.